Realistically, you have up until April the 10th, I believe, which is the last day of classes, to hand in your labs. I highly, highly recommend that you do not wait that long because at any time, um, I can invoke our and it's in our it's in the your course outline, the um, the departmental rule of you must hand in within a week or 5 days all assignments and labs. So and that would only happen if suddenly people start needing to needing help because they're getting sick, myself included, or whatever. So try to get your labs and assignments in as soon as possible. If you're sending it to wetcourse@hotmail.com, great. I am checking daily wetcourse@hotmail.com, and also checking the junk folder, um, just in case somebody's email may end up there. If you're worried that I have not responded right away, you may find that it will take a while for myself as well as other instructors to get back to you. This is not an excuse, it's reality. Unfortunately, and I mentioned this earlier, but I'll mention it again for people who just joined. Unfortunately, we're quite busy redesigning our courses to deliver online, same with all the exams, and then marking assignments. And since most people don't have scanners and are just taking pictures page by page and are not naming them as requested, it's creating quite a bit more work. We will eventually, or I will for sure get to every email, I promise you, unless something drastic happens. And I'm sure all the instructors will. Anyways, April 9th? Okay, April 9th. Whatever the date is. I'm just going by memory. Last day of the course. But at any moment, like I said, I can invoke that clause that says, no, you guys are late with labs. So please don't put me in that position. I know everybody's busy. So try to get them in as soon as possible. I said before that I wanted everything in by this weekend. That's what I mentioned before. But it looks like there are some people who are falling behind, so just get it in quickly. All right, any questions on that? Looks like a lot of people here, which is awesome. Oh, 1 second. Unfortunately, I'm losing power. Yeah, that was close. Almost lost everything. Okay, I'd just like to can everybody just put up their hand and keep it up, those that can hear me? Okay, I'm assuming that everybody can then. Yeah, you may as well put down your hand. So like I mentioned before, this is just the final review. I will post it as well as the lab review. It is optional. If you guys have lots of work, you can always look for it on Moodle. But it's a good time to ask questions. So please unmute your mic if you have any questions, or raise your hand, and I'll just go through it. Okay, so basically week 1, we just went through the vocab, and I'm just going by everything that was planned. Of course, things kind of went for a loop a few weeks ago. So it is fair game, considering this is an online quiz and exam coming up, that it's and the final exam is probably going to be open book. It's fair game for any vocab that is listed here or throughout any of the supplied materials I gave to you, anything in the course package or in the labs. So if you don't understand any of these, please ask now. Okay, I'll go on to the next one. Oh. Yes, these slides will be on Moodle. And thank you, Josh. That is exactly what I'm trying to say. Everything is fair game. So, okay, we're good on this one. Oh, man, that's bad. Okay, are we good with this one? Thanks. You know, that's one thing that I have heard from, actually, nobody in, none of you have mentioned this, but I've heard from other students and other instructors that this online delivery is painful, incredibly painful. And most people just end up recording it, watching it at their leisure, and during the time just work on other stuff or yeah, but yes, so kudos for you guys. Anyways, I assume we're all good on this page. I'm going to continue then. Okay, I highly doubt that there's any problems with any of the first five. Discrete is just on, off, and analog, of course, is, yes, that's true, Quinn. It is hard to dictate how fast or slow the class goes. And analog is basically an infinite range of values, but practically it's whatever the span is. Megan, yeah, I won't admit that I've been doing the same thing, but you know, something similar. Okay. Actually, my fear is how everybody's going to look when they haven't been able to go to hairdressers and stuff after a month. Anyways, okay, how about this page 7? Some things. I think everybody's going to be okay with this. We went through in huge detail process variable, set point, control variable, all that sort of stuff. So, yeah, okay. So no questions here. Good. I said before that, oh, it's not on here. No, next page. I think distributed control system, I think I said don't worry about it. Worry about it now. PLC SCADA, timer, counters. Yeah, this is the final lecture session with me. Well, not really true because I'm going to be hanging around on Monday for the quiz, that 2-hour quiz or hour and 15-minute quiz that you guys are taking. And then during the labs, of course, lab period, I'll just chill, help out if anybody needs help with labs, do marking online or whatever. Or it's Monday or Tuesday. Just ignore me. It's I just woke up from a nap. Not really true. I had a lecture, but it felt like a nap. Okay, anyways, yeah, so this is the final lecture, and it's just a review. Yes, and indeed, Glenn. Okay, so we're okay with all this? Good. Timers and counters, incidentally, they're you will learn them in great detail later on in what 227 when you learn industrial computer programming, so PLC programming. Will this review cover all? No, it would take 40 hours-ish. No, a bit more, 50 hours to cover all the material. So this is just the highlights, basically. Open loop control, that is automatic control. That's the automatic control loop. Or sorry, open loop is not the automatic control loop. Closed loop is the automatic control loop. SCAPs. Automatic control, we went through it in great detail last lecture again. So know the pros, cons of that, why we need it. 3 signals used in process control, HMI, types of drawings, PNIDs, BFDs, loop sheets. Oh, actually, that's one thing I did want to, excuse me, ask everybody. How was the quiz, that last quiz? It closed, or it's closing today. Not bad. I thought it would be hard. Okay, not shabby. I'm specific. I mean, it was hard. Ha ha ha. Okay. I don't think that the final 2-hour quiz is going to be that difficult, but it's going to be a little tricky. You're going to have to read and understand. Yeah, it was meant to be like a choice between 2 evils, and which one was the lesser of evil kind of thing. Yeah, yeah. Believe it or not, all the info was in the slides or in the material, or we had covered it. And there's some key things, like for instance, polarographic probes require an outside voltage or current to work, whereas galvanic don't. And if you miss that key one, you would miss that question or something like that. But and no, general, it's true. But you know, we'll see. Out of the conditions that were given, and that's the key. Anyways, I like I said, the final exam probably will be a little bit more concrete. It will they will be general questions again. Like generally, one question would be, what is the dividing line between laminar and turbulent flow, or whatever. Actually, I did think about that, Quinn. That's interesting. But even still, I figured that even with the maintenance costs, um, this one instrument is by far the most expensive right now, and things change. Anyways, and by the way, if you have a gripe of any of those, you can always just flag the question or email me. You remember what it is, and that's same with the quiz coming up in the gray. um, and it's almost like that movie, The Gray. It's kind of vicious and bloodthirsty and painful. Yeah, and that's a good point. And that's why for this 2-hour exam, just flag something that want me to review a question or something like that, and I will consider it. But there are some questions always with any exam that separate the men from the boys, the women from the girls, as mentioned, and there has to be rigor in every course. So, but I do appreciate your input. So, like I said, please flag and let me know if you think some questions are unfair, for sure. Okay, do we need a break right now? Probably not. Hey, yes, no, yes. Why don't we just take a two minute quick break just so people can grab coffee or whatever? And I'll even put on the whiteboard for those 2 minutes if you guys want. So, people, I guess we should return. It's terrible that I have to erase your guys' awesome art. All right. Yeah. If there are no questions, then let's continue. So, I'm assuming that we are okay with this sheet. Um, yeah. Then we got into calibration. Just remember, for calibration, there are key requirements for calibration always. One is you always absolutely must have, must have a standard. You must calibrate to some known standard. There must be a chain of custody. So you must always include your name, people you work with, partners' names, dates, observations, whether the calibration passed or not, et cetera, et cetera. And quite often you have to include a deviation chart just to show that the instrument is okay. So if there is no standard operating procedure, each one of these must be factored in when deciding how often to calibrate. So I'll let you guys read this, but be able know where to be able to find this information. What is required? Obviously, standard. You have to have controlled conditions. You have to have somebody who's trained, obviously, and always the chain of custody, the documentation that proves that there's always been proper calibrations done with this instrument. So we already know calibration is the key requirement in ensuring control accuracy. Two common methods: be able to explain the zero and span method and relate it back to the pressure lab that was where you had to perform the zero and span a couple times, and then the 5-point check. So how to perform one of those. And don't, well, actually, you probably won't have be able to just write down 0, 25, 50, 75, 100, but you will have choices like that. It might be a little tricky too, so read the question carefully. All right, I've already put some span problems up on the quiz. Be able to do this. You'll probably have a few of these span problems. Some will be easy. Most will be fairly easy, but some won't be. So yeah, there are some practice span problems posted on Moodle, so make sure you can do those. Same with what we covered in class. Be able to calculate accuracy and deviation. And yeah, not much to say about that. Same with gain, be able to calculate gain. Precision, repeatability, I'll probably have those stupid dartboard questions and ask you questions about that. Same with a graph like this. I'll throw on, I'll probably throw on the exam. This mainly because everybody should know it. And I think pretty well everybody got it on the quiz. So retain that information and you'll have easy marks. Hysteresis. Now, I've never asked that on a final exam before, but I think that's fair game now. You should be able to explain what hysteresis is. I should actually go over it because not everybody was in the lab. So basically, hysteresis is just it is found in certain substances. So iron, magnetism of iron ores. It is found in rubber bands. It's found in springs. And what it is where it's a nonlinear function where you start putting in an input and nothing changes, and then it slowly starts changing whatever you're changing. So for instance, a spring, you'll start putting force in and it's not deforming, and then it finally starts deforming. Same with elastic band, same with magnetism. And on the way back, you'll start trying to change things and it's not moving, and then it eventually starts going. So that's what hysteresis is. You can look it up on Wikipedia. Rubber banding. Did I have that written down? Rubber bands. If I said rubber banding, I gotta spit this gum out of my mouth. There's no need for me to be chewing my gum now. Okay. Obviously, documentation is vital for the chain of custody. Gum. I bet that has hysteresis. So all this. Yes, exactly. That's why I chew gum is good old halitosis. But anyways, so talked about turbidity, third weekish. Everybody should know what turbidity is. Know that 1 NTU is approximately 1 FTU, and that NTUs are basically the most widely used method in North America. The FTU is formazine turbidity unit. NTU should know the our nephelometric turbidity units. Should know the abbreviation for both those. This is the configuration for an absorptiometer. So obviously the light is absorbed by particles suspended in the solution. And nephelometers are the probably most widely used method of measuring turbidity, where generally the emitter and the receiver are on a 90-degree angle from each other. They do sometimes have them at 45-degree angles as well, but always will be at a 90-degree angle. They also have a new technology called a 360, and the jury's out on that one, whether it's that effective, any more effective than a normal nephelometer. All right, general rule, above 100 NTUs, absorptiometer. Below is nephelometer. And more appropriate, match the method to the site specific. Talked about cryptosporidium, the life cycle, should know that. And also typical installation, naming this. I don't know how the heck I would do that online, but somehow I'll figure it out. Probably a match kind of question. Then we did temperature. How would location affect which you use? Okay, so actually, if you decide to go into turbidity, so I would put the absorptiometer in at this in the first part of the plant, because that is where you're going to have. So you should know this. So like here, you're going to have an absorptiometer, and here you're obviously going to have a nephelometer, and variations between. So you should know this. Good question though. Yeah, then we started temperature measurement and bulb field thermocouples, infrared, RTDs, bimetallic strips, thermal wells. Everybody should know what a thermal well is. Whoever can yell it out first is going to be my favorite forever. No, that's okay. No, I take that back. Everybody's my favorite. Actually, seriously, anybody who actually has managed to be here and listen to this this lecture, kudos to you. You're for sure all my favorites. Yeah, the thermal well is what protects an RTD or a thermocouple, because they will wear out immediately in most processes, or pretty quickly. Pressure, this is from 115, of course, but what pressure is, all this must know, and exact. Yeah, for sure to these sig figs. And also include 33.9 feet of water. Yeah, okay, good enough. And even though this is an open book quiz and possibly, and it really depends on the deans, an open book final exam, you should have this all memorized. You'll need it coming up with work. Static versus dynamic pressure, head pressure. I don't know what I would ask for this. This is more Allison's domain. We'll see. I'll probably find something in the notes that I mentioned, something specific to our course. This just explains, of course, absolute versus gauge pressure versus differential pressure. Everybody should know that. If not, please ask now. Diff pressure, of course. Calibration. So we use a hand pump. Uh, so it's yeah, just a air hand air pump. There's another method is using a dead weight. So a weight just pushes down on a fluid inside here, either an air or a liquid, and gives an exact pressure. Or the most exact, the standard is generally a manometer with mercury inside. But because mercury is toxic, industry is getting away from that. Board-on tubes, how they work. Manometers, what they are. Again, generally this is filled with mercury, so we're tending away from them, but they still are in use. And you'll learn all about them later on with Allison. Menisci, how to read them. Strain gauges, what they are. So there are three methods for pressure measurement, and they are piezoelectric, strain gauge, and capacitive sensors. By far, the most common are piezoelectric, so you'll find them in generally most pressure gauges, but there are some that also have strain gauges or capacitive gauges. So you should know all three and how they work. Yeah, so strain gauge, capacitive, ceramic versus metal. Ceramic are by far the best, but they will break. Metal not as strong, and creeping memory if they rupture, kind of like overbending a spoon or something. Never be the same afterwards. Yeah, water hammer. Air on, air off. Okay, so everybody knows now to close valves, close, air on. Oh, geez. Okay, that's good. Well done, touche. Um, okay, yes. Anyways, piezoelectric pressure. I said that there are powers in crystals. So your aunt who believes in all these crystal powers and other cool things like fairies and dwarfs, she was right. There are power in crystals, and if you put pressure on a crystal, well, quartz crystal for sure, it will generate um, current, electricity, frequency. And same with if you apply current to a crystal, it will vibrate at a certain frequency. Snubbers are just mesh that will stop water hammer, spikes and pressure to protect instruments. Then we talked about flow. This is just before um, before we started having coronavirus, back when the world was almost innocent, one would say. Um, anyway, so parameters for flow, pressure, temp, viscosity, density, friction, Reynolds numbers. Um, yeah, just I don't think anybody has any questions about these. So this is the requirement for meg meters. Meg meters are by far probably the most lenient for laminar flows. So all instruments require laminar flows for accurate readings. Meg meters are they're tolerant. Whereas orifice plates, oh geez, you know what? Frank used to know the ISO standard for it, the industry standard. I believe it's like 30 diameters up and 10 down. It's pretty extreme. So it depends with every instrument. But in our course, I'll just ask about meg meter and just know that it's 5 up, 5 diameters up and 2 down. and this is the flow in this direction. I should almost have written that down. And in fact, I'm going to, I can't remember how to do it. Insert. Okay, sorry, guys. It's not, insert. I want comment, text box. Okay, if people are asleep now, I can totally understand, but considering I'm posting this on Moodle, I had better make that clear. Okay, specific gravity, talked about this. I'm actually going to mention this again just because it is a little bit, yes, Eric, thanks. It is still a little bit tricky. So specific gravity is always measured against um, the density of water. So it is almost always it's always unitless, and it's usually given as a percent. So like 0.810 I remember is oil, a certain type of oil. And if you want to find out how much what the density of oil is, you would just multiply that against the specific gravity of water, which is 1,000 kilograms per cubic meter. So the density of oil with the specific gravity of 0.810 is 810 kilograms per cubic meter. And Eric, no, I would be amazed if anybody's awake now. It's hard to stay awake. You don't have the same interaction with an online course. General types of flow meters: mass flow, volumetric, and velocity. Should be able to identify and define all of those. Mass flow is not commonly found in our industry, but you still have to know about it. And the reason for measuring mass is, of course, it is because mass does not change based on temperature. Mass is the same. So if you have a certain number of moles, that's it. Whereas if you're measuring volume, the volume can change drastically between gaseous state and solid state. So the simplest, the tried and pure, the standard is the bucket method. And technically the SI standard is liters per second, but we use everything: cubic meters per minute, per hour, per year, etc. All right, talk about the rotometer, the different types of bullets inside there, how to read them, all that sort of stuff. They're cheap, easy flow meters. Doppler technology, I talked about strap-on, ultrasonic flow sensors. They can have fixed flow sensors. They would never be mounted on the top. They'd always be mounted 3 degrees or 3 o'clock, 9 o'clock. So you have to know that, and also know that there has to be particles inside for Doppler to work. Bernoulli's can't talk. Bernoulli's law. The basic principles behind that. Orifice plates. Yeah, how they can calculate flow. Basically, Q is equal VA. Yeah, differential pressure with, we didn't get into any calculations for that. You get into that with Allison. Venturis, what they are: flow nozzles, wedge, V cones. Now all these are fair game. So some of the more detailed aspects of it, but if you know the general, you should be able to read in like uh, um, if the question is about a wedge or as opposed to a V cone or something like that. Um, it shouldn't be too difficult, but it'll be comprehensive, this exam, especially if it is open book, the final. And again, that is going to be dependent on the dean, what they decide. And it's not necessarily what the dean decides, but educational council and everybody. Pitot tubes, know what they are, how they work. Again, not often found in industry, but they are found. Um, Target flow meters, it's very simple. As the fluid passes, it will hit this target and will deflect the target, and that will give a good idea of the flow velocity. Vortex sensors found quite a bit lately in distribution, so it seems to be the latest flavor. And basically, there's a bluff here that causes vortices to form, causes the sensor to vibrate, and you can get the velocity based on that. And then our meg meters. Everybody should know how meg meters work. There is a nice little video posted in the laboratory. In the laboratory, geez, Frank's having a brain fart. Imagine that. Frank's asleep as well. In the lab review that I'll be posting on Moodle right after, that explains really nicely how meg meters work. I think everybody's got it now from all the breakouts and actually even from previous um, previous labs. Positive displacement sensors. These are by far the most widely used flow meters out there, mainly because every single gasoline vendor uses these. So gas pumps, water meters, anything that requires money to be paid. So anything that needs to be metered requires these. So they are exact. A known quantity passes every single time. Turbine flow sensors generate voltage based on the flow. So there is a little impeller inside that is hooked up to a generator that will generate a voltage based on how fast the fluid flows. And then mass flow meters. These vibrate and warp as the fluid passes through here. Not commonly used in industry, in the water industry, because it's used mostly for gas, but you have to know what they are and how they work. And of course, Coriolis effect. Doppler, I mentioned, ultrasonic. Then we started level sensors. So this was still in class. And so gauge glass, differential pressures, bubblers, floats, displacement, capacitive, conductivity, ultrasonics, radar. I don't want to ask if everybody's awake because I'm afraid nobody's going to put up their hands, so I won't. Gauge glasses. Everybody knows what they are? Good. Now we're asleep. Yes, I thought so, Ryder. I'm hoping that everybody is asleep because then this is a wasted review. Everybody knows everything, which would be awesome. And that means everybody's going to just ace this quiz coming up. And like I said, it's unless something drastic happens, it's going to be on Monday or Tuesday. Sorry, Tuesday, starting right on time. It's going to be open exactly for 1 hour and 50 minutes. Anyways, differential pressure, how it's used to measure tank level. So obviously it's on the bottom here, and using pressure is equal rho GH, that formula, it calculates, just compares it to the atmospheric pressure and calculates. Metal cells, how they work. Inside here would be a strain gauge or a capacitive sensor or a piezoelectric crystal, one of those three. Same with the ceramic cell, again, capacitive, strain gauge, or piezoelectric. Bubblers, nobody's putting out their hand. That's awesome. So everybody knows how these work. Just like blowing bubbles in your milk, you have to overcome the head pressure of the milk. Same thing. I have to overcome the head pressure, static head pressure in the tank. And as soon as one bubble is released, it reads how much pressure it took to blow that one bubble. Ball floats, by far the most widely used because of our toilets. Basically, the ball just moves up and down based on the level. It floats on top. And it is used very often with electrical switches. So inside here is a conductive fluid, usually mercury, and therefore it is getting out of flavor, mercury switches. So they used to be very common. They're not quite as common now. Yeah, just an example of how they work. Magnetic floats. Inside are a bunch of little tiny switches that interact with the magnet that floats up and down. Displacement sensors. These can be used in wastewater because you do have different levels. Displacement sensors, basically the way it works is this bar is made of a known mass, and when put into water, this liquid will displace the weight of the liquid. And so you know exactly, if you know the volume of this, you can figure out exactly what this liquid is. Same with this liquid, it will displace a known, or it will displace its weight in that liquid. And so knowing the volume, you can get the density of the liquid. And so you can use it with different levels to figure out exactly where interface is, where two different liquids meet. You lost me after liquid. Yes. I'm glad you've got a smiley face there. But know what a displacement sensor is. If you guys want, I'll write something up. Just email me some little thing on displacement, or find a good link to one. Capacitive probes. Basically, this probe acts as a capacitor. And the liquid is the dielectric or non-conductive. So the capacitive probes, there will be a lot of electrons in one plate and a deficiency on the other. And based on the level of the liquid, it will generate a voltage. Conductivity probes. Yeah, just generally allow conductivity between two probes through a conductive liquid. So it's an on-off level indicator. Sonic level, I think everybody's got that. A little piezoelectric crystal inside here generates an ultrasonic waveform that bounces off the level, and the time transit is measured, indicating or giving the liquid level. Ultrasonic level switches. So one thing I will mention, I found a really neat 15-minute 10-15-minute video that I will post on Moodle that explains all these instruments. It's well worth watching. I'll see actually if I'll just give a very, very quick preview of it right now, assuming I have it here. Yeah, unfortunately, I do have yeah, I do have, so for instance, Here's that tuning fork level sensor that I'm talking about, or whatever. So I do have it here. I will post it, and it's a really nice summary of everything that I'm saying, and it's done far easier or quicker than I do, but on a high level, um, as opposed to the detailed that we go into. So look for that as well on Moodle. Ultrasonic level switches, yeah. Basically, it vibrates at a certain frequency, and then when the fluid reaches this level, it vibrates at a different frequency. So it's like an on-off switch. And same with the tuning fork. It vibrates at a certain frequency, and then when the level reaches there, it vibrates at a different frequency. Then we got into chlorine measurement. You guys just had a quiz on this. I'm going to skip all this. You should be able to answer most of those questions. There are only a few questions, though. I think I only had 2 or 3. Yeah. And anyways, be able to answer, know where all these are. Same with the conductivity probe. Same with DO. There are a lot of DO questions on that one. Galvanic, polarographic. Know that the polarographic require voltage or current. The galvanic give out a voltage or current. Polarographic are bad in every way. They require more calibration, longer time to warm up, all that, whereas the galvanic, less time to warm up. They require less calibration. But the best by far are the optical dissolved probes. Polarographic versus galvanic, they're cheap now. Everybody's getting rid of them. So they're eventually they're going to be priceless. Nobody will have them anymore. Optical dissolved, they're computer controlled. They're the latest, greatest technology. Quite expensive, but once you have the initial layout, then maintenance is almost minimal. You'd have to change the cap probably once a year, and same with calibration once a year. So maybe a couple $100, $300 maintenance. Mind you, electricity costs and all that. So, I don't think it'd ever pay for itself. You need the equipment, but I guess over 40, 50 years, you might actually save money. Know how they work. Exciting the electrons around the oxygen molecules surrounding the probe, and when they return to their normal state, their normal level, they emit a photon, which fluorescence. Know about the purple light and the red light. The reasoning for that: the red light is just a timing light to help with constant self-calibration. Process control definition is control of a process. And we went through this in great detail just last class. So you should be able to define process control, know what open loop control is, manual closed loop control is. Yeah, be able to take one of the labs. So I should be able to give a lab and be able to describe exactly what each one is. So for instance, if I say the temperature lab, that's a great, easy one. You should be able to say what the actuator is. In that case, it's the solenoid. What the sensor is. In that case, it is the thermocouple inside the thermal well. What the what the process variable is. That is the temperature of the pipe. So the pipe is being heated up. So anybody should be able to do that. Yeah, so know that three major components of a automatic control loop are you have to have a sensor, a controller, and a processor that will compare the sensor and the set point, and then the final control element, which will control the process variable. Change the process to alter the process variable. So everybody should know all these. Just read it. If you have any questions, let me know, please. Okay, good. I said that this was going to be on every single exam, and somehow it's going to be on this exam. This one is not very good, though. What can somebody please unmute their mic and tell where Frank has messed up with that one? Anybody, please? Come on. Because Frank doesn't know. I need help here. Help, please. Yes, Ryder. Amazing. Nailed it, man. So I do apologize. I am going to update this right now. This one was an old one that I used back when I wanted, I thought, it's too hard for everybody to memorize all this extra stuff. But now everybody has to, because it's going to be open book, and you are required to memorize it. So know what the error is, know what the manipulated variable is. So that is the actual thing that the actuator is changing. If it's a solenoid, it would be the flow of a liquid. If it's a pump, well, it'd be flow of liquid too. If it's a gas valve for a furnace, then it would be the temperature in the furnace, etc. The process is whatever you are measuring your process variable in. So the process might be a great big tank, and the process variable might be level, or might be temperature, or might be the viscosity of the liquid inside that tank, whatever. And I think everybody else has set point error. It's the difference between sensor and the set point, and the controller just looks at the error and causes the actuator to change based on their scams. I hate this word, but set point, controller, actuator, process, process variable, and sensor. That's how I had everybody, or well, I didn't come up with it. Somebody came up with it. Scams. Set point, controller, actuator. Oh, scams. I get it now. Eric, Frank is asleep. I like yours. Okay, enough of that. Darn it all, I can't ask questions based on this, because even look at different ones. Oh, I don't have them both down. Even in my notes, they're slightly different. But everybody should be able to identify this line, and this line. And should be able to know that this is a valve, not just a gate, valve generally. This is a check valve because it has an arrow in it. And there is one other that, excuse me, looks like this. And this is a type of control valve. So technically it's a pneumatic valve. So you'd have pipe come in here, pipe come out, and you'd have air coming out. Pneumatic. You got it. Yes, so it's called control valve or pneumatic valve, diaphragm valve. I mean, it's quite different from this type. Um, yeah, know all these, of course. All these. Know what an I to P, P to I is. Know what an SV is, solenoid valve. Quite often you'll see that. Know that a P by itself is quite often called pump. All those are special, but um, I mean they're not part of the industry standard, but they're sort of accepted uses. Uh, all the labs. So not just what I've written here, all of them. Go over the lab review. Breakout assignments. Now, I only accepted the first 3 assignments and breakouts. It started getting chaotic after 4, and I don't know how I would ask any questions about the breakouts or assignments. Just generally read them, go over. And that's about it, men and women. The safety review. You have to know that, of course. And no, and you know what, Megan, I may not. And the reason is, and I do apologize, I'll probably just give everybody, boom, massive marks. Nobody loses any marks or whatever, just because they're at the college and I may not have access to them. I do right now, but we'll see. So, and I've got more important fish to fry. In fact, great big honking whales size fish. But sorry, I was whining out loud. Any questions on this review? Cool. Well, everybody, that's it. This is technically the last lecture. Thank you for allowing me to double up on the labs. That was fantastic. Um, Next lecture is not a lecture, it's going to be the quiz, 2-hour quiz. I'm still going to be on for the labs that week, though. If you guys have any questions about writing the labs, get everything in, please, as soon as possible. And yeah, be safe, everybody. Stay isolated, try to stay sane, and good luck. And what's a breakout? Haha. Just like another class was asking, what's quiz 1? We didn't have any quizzes in that class. Where's my quiz 1?